Yeah, my name is Kuanysh, and I want to take this opportunity to talk to you about carbon textile reinforced mortar, the masonry bond. Uh, just before we start, my presentation is divided into four parts. I will start with the aims and objective. Then we will look at methodology, experimental program. Next, move to the result and discussion. And finally, I want to conclude and speak a little bit about future work. Uh, Just before we start, I want to explain what textile mortar is. Uh, in common, it is comprised the textile material. It could be basalt, carbon, or glass, etc., embedded in a mortar matrix. This technique is successfully used for straightening, reinforced concrete, and masonry structures. Uh, The aim of the experimental campaign is investigate the bond among the mortar and organic matrix, chain reinforcement, textile, and the substrate masonry, and understanding the bond behavior and between TRM and masonry can be used to design guidance of strengthened masonry structures. We experimentally investigate the bond between TRM composite material and brick masonry walls. The investigation parameter included bond strength on the bond strength. In this work, we used carbon textile with mesh size of 8 millimeter in both sides. Here you can see the property of the material according to manufacturer datasheet. It is noted that the textile fiber thickness was calculated based on equivalent smear distribution, the ratio of aerial weight to density of fibers. Additional to that, all textile was coated with epoxy resin with the following procedure. The textile was cut in strips with normal dimension within 120 millimeters and length 1000 millimeters. Then the textile was placed flat onto a workbench, taped to prevent slip, and painted using a roller with a foam nose. The textile was left in a lab for 2 days to cure, and only after that they moved to straightening. Masonry valid. It's a typical clay brick. We use it with a nominal dimension of 250, 125, and 65 millimeters. Here you can see the flexion compressive strength of casting mortar, and the strength in mortar was a cement-based mortar and an organic dry binder comprised cement and polymers at a ratio 8:1 by weight. On the next slide, I want to talk a little bit about mortar we're using for straightening. As you can see, we have a 4 mortar, M1, M2, M3, M4, and the main differences between mortar M1 and M2 is actually the same mortar as we talked before, the previous slide. And the main differences is just using the mortar ratio of 0.23, and after that we decided to artificially improve mortar features by just decreasing the water-mortar ratio. And then we use 2 high-performance concrete in-house made mortar. And here you can see the content. The main differences of between them is the presence of basalt fibers. Straightening procedure. The first stage, the dust removed, and first layer of mortar was applied. Then the textile was put into position by hand pressure, and finally the last steps. It's when the final layer of mortar was applied. The standard single lab test, we use according to recommendation Real Technical Commit 250. And here you can see the number of spacement, the spacement we're using. As you can see, the main differences of them is using the mortar matrix, and the bond length is constant and comprise 150 millimeters in each case. In each case, we use 3 samples. The naming convention is XV1M, where the X corresponds to the textile fiber material, in our case carbon, V1 corresponds to the bonded length, and M corresponding to the mortar matrix. The suffix K is added just to say that the textile was coated with epoxy resin. Experimental setup and the spacement was fixed between 2 rigid steel plates with dimension of 60 to 500 millimeters. The 2 plates were connected through 4 steel rods to ensure that the wallet would not move upwards during the load application. And the bottom part plate was fixed with to the floor with a free length of 400 millimeters in all spacement. The textile was connected to the actuator using 2 steel plates. Rubber pads was used at the textile to steel interface to improve gripping system to avoid any movement and damage of textile. 2 linear variable differential transducer with a maximum stroke of 15 millimeters were directly attached on the wall, and 2 similar LVDT were used to measure the relative displacement of the textile to the wall. The load slip response was recorded with a fully computerized data acquisition system with a constant rate of 4 Hz. The load was applied using 100 kN hydraulic actuator, and the loading rate was equal to 0.3 millimeter per second. And as a result, we can see here in this table that the mortar, when we change mortar, it's not a very high effect on the maximum applied load. However, we can see that the failure mode is different. For example, in case of M1 mortar, we see the detachment matrix to matrix interface. In case of M2 mortar matrix, the failure is again detachment, but with a part of the sliding of the textile with a mortar matrix. In case of mortar matrix for M3, we have sliding and tensile failure of textile out of the matrix. And finally, M4 mortar matrix will have capacitive debonding in the substrate. On this slide, we can see the differences between when we change the water-mortar ratio. As we can see here, in case of M1 mortar, the load applied linearly up to the peak load and then sudden drop. So it happened when the textile detached completely. However, in case of when we change the mortar matrix to M2 mortar, we can see that firstly, the displacement decreased almost for 50%, and the detachment was secured only partly, and then the remaining part was sliding, and in this case we have something like residual strength, which we don't have, and we can see that the load applied with different with steps, let's say. Okay, and when we compare a foam mortar, we can see that in case of M3 mortar, this is just to remind you, it's in-house made high performance concrete mortar. We have a sliding of the textile, and the straightening part was cracked, and the detachment worked only partly, and again after that the remaining part can resist of the load to the load. However, when we change more, we just adding the basalt fibers, we can see how the failure mode changed cardinally. We see that we have a detachment with a subtract. In this case, we can explain that the fibers work as anchors, and they have better, let's say, performance and better adhesion between textile and mortar. And of course, the last mortar M4 have the highest maximum load and the lowest displacement compared to others. So in conclusion, I want to say the first thing, for the case of M1 mortar under investigation, the effective bond length is higher than 150 mm, and mortar cannot fully utilize the fiber potential. In case the M2, M3 mortar, failure occurs in multiple phases, following step-by-step fracture of the mortar matrix. All specimens demonstrate some residual strength prior to the total textile detachment. This is not the case in M1 mortar, where the failure is rather sudden. Fiber presence in case of M4 mortar demonstrated promising alternative to the M1, M2, and M3 mortars, the same bond length. The mortar shows proper adhesion between matrix and textile. This can be explained as randomly distributed fibers in the mortar matrix allows textile with matrix as an anchor. And the bond between TRM and substrate becomes a weak link in the stating technique. As a result, all specimens treated with M4 mortar fail due to debonding at the matrix to substrate. It shows the need to subtract should also be prepared before straightening. And in the future work, we want to investigate the bond between masonry and TRM straightening with other textile materials and working with a different condition, and of course with different mortar matrix. Thank you very much for your time. If you have any question, I will be happy to answer.